as I said before, for most of the history of astronomy, the only planets that anybody knew anything about were those planets in our own solar system. So we have our planets in the solar system, and they were thinking planets might form around other stars, but they weren't sure. They had all kind of different ideas about how planets might have formed, but the problem is we didn't see any planets around other stars. As I said, they are very, very difficult to see. Astronomers were arguing about how frequently they may have formed. For example, some said, like Otto Struve, that all stars probably had planets. Others said, no, it's a really unusual sort of situation, so only a very few stars have planets. And until you start seeing planets on other stars, you don't really know. As I said in the previous lectures, Otto Struve was really the key for American search for extrasolar planets. His theory was that the accretion of the star would create the conditions necessary for planets to form. So he thought that practically all solar type stars would have planets. Now, he wasn't entirely convinced that binary stars could maintain planets, nor that really large stars or really small stars, but all the medium-sized stars, like the sun, that formed should have planets as a byproduct of star formation. Now, that was his idea, and Otto Struve was a very well-known astronomer, but no one had ever seen a planet around another star until the mid-1990s. This was almost 30 years after he died that the very first announcement was made of a planet orbiting another star. That discovery was made by Michel Mayor and Didier Queloz. They're from the University of Geneva, and they made this announcement in 1995. They were studying the star 51 Pegasi. Now, remember, that's a star name. Remember, beginning of the semester, we talked about Flamsteed numbers. This is one of the reasons I have you study Flamsteed numbers is that the Bayer designation with the Greek letter and the constellations, one way of naming stars. The other way of naming stars with the number and constellation turns out to be very important, so you understand what that name means. So 51 Pegasi, it's star number 51 in the constellation Pegasus. Now, the thing is, this planet was pretty big. It was about half the size of Jupiter and was orbiting a star, but it was orbiting very, very close to the star, at a fraction of the distance that Mercury orbits from our sun. That's way too close, according to theory, for a big planet to form. Well, that's okay, because we think it might have formed further out in the accretion disk, and then the frictional drag of moving through the accretion disk may have caused it to spiral inwards, or it could have interacted with another planet, and the gravitational interaction could have made it go inwards and the other planet to go outwards. By the way, they just made this discovery in 1995, but they were awarded the Nobel Prize in Physics for this discovery in 2019. So that's a long time later. So it's like almost 25 years later that they got the Nobel Prize for their discovery. And sometimes these awards come much later than you would think they would. So now we want to say, well, now we want to ask, how did they discover a planet? Because we already said that finding a planet is very, very difficult around another star. Remember, I said that finding a planet is not really a confirmed discovery. It's just, something you say you think you found it. Well, Jeff Marcy and Paul Butler at University of California, Berkeley were working on a very similar project to what the Mayor and Queloz team at University of Geneva were working on. And they looked at the data that the other astronomers had found, and they confirmed, in fact, there was a planet signature around the star 51 Pegasi. Shortly thereafter, they announced their own discovery of a planet around 47 Ursa Majoris, and then not too much later, a planet around 70 Virginis. So Marcy, Jeff Marcy, led a team here that actually made a number of important discoveries in the early days of studying extrasolar planets. So how do you find these extrasolar planets? Well, one way that that's done is the Doppler shift. So what happens is that you have a planet, and the planet is going around the star. So the planet's going around the star, and the star is also moving. So what happens is the planet is moving, the star moves, and so they both have gravity acting on each other. And so the star going around the planet causes the planet to wobble a little bit. So that means from an observatory on Earth, you'd be looking at the planet, and sometimes the planet would be coming towards you, and sometimes the planet would be going away from you. And you could see it blue shifted and red shifted. And so that would be this planet going around, the star wobbling. The star doesn't wobble very much. Doesn't have to wobble very much. Just has to wobble enough to be measurable. Now, the problem is that in order to wobble enough to be measurable, then it has to move pretty fast, which means the planet has to be in a very close orbit, and it has to be a very big planet. So that means that this technique would not detect Mercury orbiting the sun because it's too small to make the star wobble, and it would not detect Jupiter orbiting the sun because Jupiter is so far out it takes 12 years to go around. And so in that case, the star would not be moving very quickly. And so this technique is sensitive primarily to detecting really big planets really close to stars. And so that's not really what we expect most planets to be like. You know, we normally expect the big planets to be out far from stars. So this is probably detecting the odd planets, not the most common planets. In fact, that's kind of what happened. 51 Pegasi goes around very quickly right here. 47 Ursa Majoris, that was the star that Jeff Marcy discovered a planet around too. And so both of these were very close in. 51 Pegasi was about half the mass of Jupiter, but was about a tenth of an AU from the star. Well, a tenth of an AU didn't make any sense because that's closer than Mercury. Mercury orbits about 0.4 AU. And so this was closer than planet Mercury is from the sun. And so how do you get a gas giant up close? Jeff Marcy's was about 2.5 times the mass of Jupiter at about 2 AUs. That's only a little bit farther than Mars. That's still a little bit closer than it should be. So what happened? Well, this was a big confusion for astronomers because once they realized that you could find find planets on stars this way, other astronomers started looking, and this graph here actually comes from the early days of finding planets around stars, and what they found were most of these were gas giants that were up close. Well, think about it. What makes it easy to see a fast-moving star? What makes a star fast? Big planet up close. Jupiter is 5.2 AU from the sun, takes 12 years to go around. Well, think about it. How fast does the sun move if it wobbles in 12 years? Well, not very fast, which means we wouldn't even have the technology to find a Jupiter-sized planet at Jupiter's distance from the sun. To find a Jupiter-sized planet, find that wobble would have to be up close. Mercury goes around a lot quicker than the Jupiter. Mercury goes around in 3 months. But Mercury is so small, it doesn't pull on the sun enough to be measurable. At least not from a long ways away, not by Doppler shifting. So the technology would not see a solar system like ours. it would see these the kind of things. And so I know that some people in the early days started suggesting maybe the solar system is odd because we have these rocky planets up close and get gas giants further out. I don't think that's the case, and most astronomers today don't think that's the case. We think this is an example of what we call the Momquist bias. The early stars were primarily gas giants up close, the ones that we found. Our current understanding of how star formation and planet formation works is that the big planets ought to form farther out. Now, we do know that Jupiter moved in closer and Saturn moved out. Well, what if Jupiter and Saturn were much closer to each other than they were in the solar system? Then Jupiter would move much closer in, Saturn would move much farther out. That would put a gas giant really, really close. What if Jupiter formed farther out than Saturn? Because Jupiter's bigger, it would push Saturn even farther inwards. And so, again, that would be an example of how a gas giant got really close like that. In fact, there's evidence, if you look at the spectrum of certain kinds of stars, their spectrum indicates like dusty stuff in the spectrum, as if a planet had run into the star. You'd expect that, if in fact this kind of migration pushes a planet into a star. Okay, so the Momquist bias, we talked about this before. It's named after Gunnar Momquist, who stated all the way back in the 1920s that sometimes what you see is not the most common thing. You see what's easiest to see. So the easiest thing for you to see is not necessarily the most common thing. So he was referring this to stars in general, that the kinds of stars you see in the sky are not the most common, but they are the biggest and brightest because they're the easiest to see. You can see them halfway across the galaxy. So of course you see them more often than you do the small dim one, which are more common. Likewise, you don't see the most common kind of extrasolar planet or exoplanet. You see the ones that are easiest to see. So that would explain the entire early results that they were finding, and that was giant planets up close, because that was what the technology was able to see. So again, this is an observational bias. A planetary system, kind of like our solar system, would be almost impossible to detect with the current technology that we have. So the planets that we see are obviously not going to be kind of like the solar system. So they actually have a term, hot Jupiter, to describe these gas giants that are up really close.